Hello everyone. In this session, I will share with you the application of the Laplace transform in electrical circuit system. I will discuss with you the circuit analyzed in two different ways. The first, we govern the circuit into a differential equation and solve it by using the Laplace transform. And second, we draw an equivalent circuit in the domain S and find its inverse of Laplace transform. Before we can discuss the circuit in two different ways, first of all, we must know what is the basic component in this circuit network. Okay. The basic electrical circuit system consists of the resistor, inductor, capacitor, and the source. Okay, this is the symbol for the resistor, inductor, capacitor, and the source. Okay, unit SI for the resistor is ohm, and unit resistor for the inductor is H, capacitor is farad, and the source is a volts. Okay, then normally you will find the voltage drop across the resistor. That is VR equal to IR. This is so-called the Ohm's law. Or the inductor, the voltage drop across the inductor. That is the VL equal to L di over dt. Or the voltage drop across the capacitor. We name it as I equal to C dV over dt, or the voltage drop across, that is ET or VEMF. Now let's look at the example 4.28. Figure beside show an RL circuit with the L equal to 1 H, R equal to 2 ohm, where the switch is switched from the A to B at T equal to 0. Find the current IT through the inductor as a function of time. Let's sketch the graph of the IT versus T. In order to solve this question, we can use the Kirchhoff voltage law, KVL, to find the voltage drop across the inductor plus the voltage drop across the resistor equal to the ET. So as you know, the voltage drop across the inductor is L di T over dt, and voltage drop across the resistor is ITR, and the source ET is still ET. Okay, and do you still remember what is the initial condition of the circuit? Okay, the question said the switch from the A to B at T equal to 0. This means that T less than 0, okay, for the voltage here, T less than 0, you have the voltage is 4. For T less than 0. And then for T more than or equal to 0 is 0. The so-called the switch is switched from A to B. Okay, at T equal to 0. So after T equal to 0, the switch to B. Means that it switched to B, there's no voltage here. So before it switched to B, then there's a voltage of 4. So this is the value for the voltage, the condition of the voltage. And we substitute the value of L, that is 1, and the R is 2. So you have dit over dt plus 2it. Now we can Laplace transform of the dit over dt plus 2 Laplace transform of the it equal to Laplace transform of 0. Do you know why Laplace transform of this is equal to 0? This is because we only find the Laplace transform for t more than or equal to 0, since the Laplace transform is not defined for the negative t value. Okay, so we only Laplace transform for this one, so Laplace transform of 0. And 4 is not counted. For the Laplace transform of derivative, we can go back to the Laplace transform derivative table. Okay, so the Laplace transform of yt is equal to ys, and Laplace transform of y prime t is equal to sys minus y0. Therefore, we get sis minus I0 plus 2is equal to 0. Laplace transform 0 equal to 0. For this one, assuming the circuit was in steady state for t less than 0, it brings that for t less than 0, for V equal to 4 volt and the R equal to 2 ohm. So therefore the I0, when I0, that is V equal to R. So I equal to V over R. V is 4, R is 2, which is equivalent to 2. Okay, so I0 equal to 2. So we can substitute in here. So I get SIS minus 2 plus 2IS equal to 0. So we take out the IS, which is equal to S plus 2 equal to 2. We bring to the right hand side. And IS equal to 2 over S plus 2. Once you obtain the IS, okay, we can obtain the IT from the inverse Laplace transform of the IS. That is 2 over S plus 2, which is 2 is the constant, we can take it out. So it's equal to 1 over S plus 2. This is equivalent to 2 exponent negative 2t. So for t more than or equal to 0, IT is 2 and t less than 0. For t less than 0, the value is 2. And for t more than or equal to 0, you have the value of 2 exponent negative 2t. This is for t more than 0. Okay? So when you plot a graph, it looks like this. So before less than 0 or t less than 0 is the value of 2, and after t more than or equal to 0, you have the 2 exponent negative 2t. Okay, this is the graph. Now let's go to another example. Figure beside shows an RLC circuit with L equal to 0.25 H, R equal to 0.1 ohm, C equal to 2 farad, which is initially at rest. A power source of 1 volt is applied to the circuit for 10 seconds. Okay, first determine the current IT in the circuit. Then, by using the software method, plot the graph of IT versus T for T less than 0, for T less than 35 and more than 0. In this question, we find, using the KVL, we find the voltage drop across the inductor, plus with the voltage drop across the resistor, plus the voltage drop across the capacitor equal to the ED. So here, voltage drop across the inductor is L DIT over dt, plus the voltage drop across the resistor is plus ITR, plus voltage drop across the capacitor is equal to 1 over C, the integration 0 to T I tau d tau equal to the ED. ED in the questions, the initial condition is a power source of 1 volt is applied to the circuit for 10 seconds. This means that 1 for t less than 10 and 0 after t more than or equal to 10. So then we substitute the value of L. The value of L is equal to 0.25, R is 0.1, and C is 2. So 0.25 DIT over dt plus R is 0.1 plus C is 2. Then I tau d tau equal to, okay, this one we can refer to the step function to get the unit step function. That is 1 plus 0 minus 1 ut minus 10. Okay, 1 plus 0 minus 1 ut minus 10. Okay, and then we can simplify again. We get 0.25, and then Laplace transform of dit over dt plus 0.1 Laplace transform of the it plus 1 over 2 Laplace transform of the integration 0 to t I tau d tau equal to, okay, here I write it down, Laplace transform of 1 minus Laplace transform of the ut minus 10. So by this side, this one, we can use the transform of integral. Okay, using the transform of integral, we obtain, this is called transform of integral. We Laplace transform of the fs divided by s, can obtain 0 to t f tau d tau. So therefore, this part we can get for the Laplace transform of the 0 to t I tau d tau, you can get is over s. Okay, start from here, is over s for this part. So therefore we can simplify, and this part we can get Laplace transform or derivative, so we can obtain 0.25. Okay, Laplace transform of dit over dt, we can get s is minus I0. Okay, then plus with 0.1 Laplace transform of it, we obtain the is plus with 0.5, and then we obtain this is over s, which is equivalent to Laplace transform of 1. This is, you can refer to Laplace transform table. A, you can get a over s, so it's 1 over s. And then Laplace transform of ut minus 10. Here we can get s1 minus 10s over s. Okay, so I multiply in, I can get 0.25 s is. Okay, for the I0, RLC circuit is initially at rest. So the question is the RLC circuit is initially at rest. So I0 is equal to 0. So this is equal to 0. So you can substitute here 0, you can just left nothing here. And then plus with 0.1 is plus 0.5 is over s equal to 1 minus s1 minus 10s divided by s. And I take out the is, and I left 0.25 s squared. Okay, so this is the s here, right? So I can synchronize all the s. So I multiply with the s. This one also the same. This one I multiply with the s, so I can cancel out the s here. So plus with 0.1 s plus 0.5. This is equivalent to 1 minus s1 minus 10s. So this s also cancel out. Now I have the is equal to 1 minus s1 minus 10s divided by the whole thing here. I can divide. So 0.25, so I get 1 over 4 s squared plus 1 over 10s plus 1 over 2. Since the denominator is 10 and this denominator is 4, we can synchronize the denominator by multiplying. This is multiplied by 5, this one multiplying with 2, so we get denominator is 20. And then this one multiply with 10. So I get 1 minus exponent minus 10s divided by, this one multiply with 5, so I get 5 over 20 s squared. And next one I multiply with 2, so you have 2s divided by 20. And this one is multiplied with 10, so I have 10 over 20. So when this one I bring up the 20, so I have 20 multiplied with 1 minus s1 minus 10s divided by 5s squared plus 2s plus 10. For this denominator, we can solve it in this way. Okay, 5s squared plus 2s plus 10, which can be factorized like this. 5, we take out the 5. So you have the s squared plus 2s, okay, 2 over 5s plus 2. So we can rewrite into this form. We factor out the 5. Okay, we factor out the 5. And then next, okay, how to factorize this one? Okay, after we factor out the 5, how to factor out this equation? Okay, we can factor out like this, 5. How to get 2 over 5? This means 2 over 5, that is, we factor out like this. One is s squared, so it means it's s and s. And factor out 2 over 5s, that is 1 over 5, 1 over 5. So you can get the 2 over 5. So, okay, if you use like this, for example, if you have s plus 1 over 5, multiply with s plus 1 over 5, what do you obtain? This equation, we can get s squared plus 2 over 5s plus 1 over 25, right? Okay, this equation we can get this. But if you look at the original question, the value that you want to get is s squared plus 2 over 5s plus 2. But from here, you only get plus 1 over 25, which is not the same like 2. So you need to cancel out this one plus with 2. Therefore, I minus with 1 over 25 plus with 2. So I can get back the same value here. Therefore, I can have a 5s plus 1 over 5 squared. Okay, and then we settle this one, 1 over 25 plus with 50 over 25, because it's 2, right? So we get plus 49 over 25. Since we have settled this part, so we can substitute back to here. Okay, this is about the IS, this is for the IS, so we can substitute this part with this value. Therefore, okay, if you have the IS, we can find the IT. Okay, we inverse Laplace transform of the IS, we can get back the IT. Therefore, we get inverse Laplace transform of the IS. We can get 20 over 5. Okay, we substitute this equation into here. Okay, so you have 20 over 5 inverse Laplace transform of 1 minus exponent minus 10s divided by s plus 1 over 5 square plus 49 divided by 25. So 20 over 5. Okay, this is the operation of minus. So we can split it into 2. So that is inverse Laplace transform of 1 over s plus 1 over 5 square plus 49 over 25 minus inverse Laplace transform of exponent minus 10s divided by s plus 1 over 5 squared plus 49 over 25. Going to 20 over 5. So for this one, inverse Laplace transform of this one, we can have the exponent. This is based on the table of Laplace transform. So you can have the exponent minus 0.2t and then inverse Laplace transform, and we left s squared plus, okay, can we square root of this one? If we square root, this is like a form of the, okay, this is like a form of sine. So we square root of this one, we can get 7 over 5 square. Okay, and then minus with the inverse Laplace transform of the exponent negative 10s divided by s plus 1 over 5 square plus 7 over 5 square. To change to the sign, here must also same with this one. So numerator here must also multiply with 7 over 5. But to multiply with 7 over 5, this is not the original value. Again, if you want to cancel out this 7 over 5 value at the numerator here, so we need to multiply with 5 over 7 to cancel out the value of the numerator here. Therefore, I need to multiply with 5 over 7 to cancel out the 7 over 5. Okay, and this part we can do it using the second shift theorems. So I'll copy down this one first. So to do this part we can solve using the second shift theorems. In which there is the exponent negative s divided by the s plus, this is for the s square, s plus 1 over 5 square plus 49 over 25. Okay, so second shift theorems, we must follow the procedure or the step to calculate. So the first step is to find the a. So step 1 is a equal to 10, which is from here, this value. And then step 2 is to find the fs. So this part will be the fs. So this is equivalent to 1 over s plus 1 over 5 square plus 49 over 25. Then step number 3, we want to find the ft by using the inverse Laplace transform. So inverse Laplace transform these holdings. So 1 over s plus 1 over 5 square plus 7 over 5 square. So this part, if you want to have a sign, so make sure this one you need to have a numerator as 7 over 5 too. But to cancel out this value 7/5 because the original value is 1, and you get 7/5 just to fulfill the sign form of the Laplace transform. And then you must multiply with the 5/7. This is because 5/7 and then multiply with 7/5, you can cancel out. Okay, so this means you have multiplied with 5/7, and then this s plus 1/5, you can change to the exponent negative 0.2t, and then inverse Laplace transform of 7/5 divided by s squared. So once this one's change to exponent negative 0.2t, and this part we left the s squared. Then plus with 7/5 squared. This is equal to 5/7 exponent negative 0.2t sine 7/5t. Then step number 4, we change the t to ft minus a. So therefore we have a 5/7 exponent negative 0.2 t minus a. Now what is the a value? A is 10. Okay, a is 10. So t minus 10 sine 7/5 t minus 10. And then step 5, we inverse Laplace transform everything, and in the end we get 5/7 exponent negative 0.2 t minus 10 sine 7/5 t minus 10 u t minus 10. So step 5 is to add the u t minus 10, in which we add up the unit step where the t value, the t minus the a is referred to the a value that you obtained from the first step. So now we can complete the final answer. So therefore, IT that we can obtain is, we can starting from the here. Okay, this for the first part we copy it down from here, and then the second part you get the answer from here. So therefore you have 20/7 exponent negative 0.2t sine 7/5t minus with 20/7. Okay, 20/7 because 20 is from the first part. Okay, 20/7, the 20/5 multiply with the 5/7, so you get 20/7. Okay, exponent negative 0.2 t minus 10 sine 7/5 t minus 10 u t minus 10. That is how you solve the application question with knowledge of the unit. You need to know what is the component representation in the inductor, resistor, and capacitor, as well as you need to use the transform of integral or Laplace transform or unit step. Okay, the derivative formula, and also the second shift theorems, and how you use the Laplace transform table to help you in convert to the IT from the IS. So this question is a combination of all. So therefore you must understand how to convert or how to use the property of each Laplace transform in order for you to solve the question. That's all how we solve the circuit analysis in the differential equation and solve it using the Laplace transform. Thank you.